Okay, so what we've arrived at here is that really the only thing that matters in determining the period of a pendulum is the length of the pendulum, all right? And with that in our back pocket, we're gonna start investigating what the motion actually looks like. And we could look at a bunch of different things, but what we're gonna focus on first is position. And then ultimately what we're gonna do is we're gonna try to tie that into both the period and the length. Because ideally what we could do is just use, since the length is going to determine the period, ideally we'd be able to use the length to determine like the position and velocity and acceleration of that force as a function of time. So we'll look at all of those things down the road. What we're going to start with today is two things that are relatively straightforward. Okay, the first is that I'm going to ask you to just look up the actual equation for the period of a pendulum to make sure that it matches up with what you're seeing. And what you'll find is it does match up, although there's a couple things that are weird about it. One is that there's a square root involved. So it's not a direct, like it's not directly proportional, it's directly proportional to the square root of the length. The other thing you're going to see is 2 pi. 2 pi is in there. And that's kind of weird because like 2 pi means, 2 pi tells me something about circles, right? And it sort of makes sense, like, well, it's moving along the arc of what would be a circle, but if you think about its actual motion, there's not really anything circular about this. So the 2 pi coming in there is a little bit weird. We're gonna watch a video later that will explain a little bit of that. For now, what I want you to do is just look at the equation for period, make sure that it makes sense to you, that it matches up with our observations from the work that you just did. And then the next piece is I want you to make a position versus time graph. So you'll be measuring the location of your pendulum as time goes by and making a graph of it. And you should already be thinking in the back of your mind, well, it's gonna be sinusoidal. It should be a sine curve. And here's where I just mentioned that pendulums aren't perfect simple harmonic motion machines. So we're gonna start looking at that right now. And we'll fill in some gaps today. We'll fill in more gaps on Friday. But basically what it boils down to is it all has to do with this diagram, which, okay, it's not perfect. There's a bunch about this that isn't perfect, but there are a few things that we can see really clearly. If we were to just look at the motion of this pendulum from, say, this extreme position, let's say this is its starting point, and it moves down to here, we can think of that motion in a variety of different ways. Okay, one way is we could look at this angle. Okay, that's how far the string moves in terms of change in angular position. So we could look at the angular displacement. The other thing we could look at is the arc length, which would be the distance along the curved path between where this thing starts and where this ends, which is obviously going to be related to the angle, because the larger the angle, the larger the arc length. Both of those things are, like, we could measure them. They're not impossible to measure. But actually, there's a couple of things that would be easier to measure. One is, we could just measure the linear displacement. We could look at how far it is in a straight line between where this thing starts and where it ends. And that's not really how far it moves, is it? But it's pretty close, at least under some conditions. So if we were to just think about the distance, this length of this green line is going to be really close to the length of this curved orange line. Or we could even look at it in terms of vertical and horizontal motion. And we could look at what its horizontal displacement is as it moves from its initial to the middle position, or we could look at its vertical displacement over that same time period. If we think about the horizontal displacement, then we can think about, like, we could put a ruler under it and we could just measure its motion on a ruler. There's some good reasons to use this value over all the other ones, okay? it's easier to measure this than the linear displacement. And it's easier to measure linear quantities in general than it is to measure angular quantities. The length of this blue line is going to be about the same as the length of this green line, which is going to be about the same as the length of this curved orange line. Are they exactly the same? No, they're not. But it turns out that if we keep this angle less than about 20 degrees, then they are almost identical. Okay? In fact, less than 5 degrees, and like astrophysicists and a lot of other physicists will just say it's the same thing. The difference between the arc length and the chord length and the horizontal displacement are so small at an angle under 5 degrees that it's not even worth doing the calculations. And that we'll look at a little bit more on Friday. It's called the small angle theorem, and like it's like so ridiculously accurate that it's a wonder that we even bother to measure angles that are less than 5 degrees. So this is how I'm going to recommend looking at your displacement. And that means a couple of things for your position versus time graph. One is, the way to measure it is to put a ruler underneath, and I don't have one because somebody took it, but there's a ruler here. Well, here, we can pretend this is a ruler. So you put that underneath your pendulum, and then hold the pendulum up, like hold it up above 50 or something when it's at its equilibrium position. And then you just kind of look down and you lift it up to a certain position and then let go. And you just measure where it is on the ruler relative to that middle position. So I would say, like, what's easiest for me to think about is the middle position being 0. So this might say 50 centimeters, but we'll call that position 0. And then positions to the left of that, we could say, are negative. So this might be negative 0.31 meters. Positions to the right of that would be positive. So this might be 0.31 meters in the positive direction. And I don't know exactly what yours is going to turn out to be. It depends on how long your string is and how high you decide to pull it. But if you keep these angles at less than 20 degrees, you can use this distance in place of the angle, the chord length, the arc length, or the height. And all of those are a little bit more difficult to measure and don't really give you anything in terms of additional accuracy. So this will be how we look at the motion, the distance, the location of your pendulum. So what that means is what you're gonna be graphing is effectively something that shows horizontal displacement in meters ideally, although it doesn't have to be meters, and time. So the horizontal displacement will be on the y-axis, time will be on the x-axis, and this is gonna reflect one full period. So this will be like half a period. This would be a quarter of a period. This would be a quarter of a period. Or I guess that's 3/4 of the period. And then we can picture where this thing is going to be at various times, right? So if we start it at its fully left position, that's going to be negative, right? So that's going to be negative, like whatever the maximum horizontal displacement is. And then we're going to let go, and it's going to move to the equilibrium position, which is 0. And then it's going to move to its maximum positive displacement, and then it's going to move back to 0, and then it's going to move back to its maximum negative displacement. So it's going to move from its maximum negative displacement to positive, to negative, to positive, to negative, to positive. And every time it swings, it moves a little bit less far. So it's not going to be perfect. It's not going to match up perfectly, but it'll be pretty close. And what I would recommend is take a video of this with your phone up above, taking the video from above, and then what you'll be able to see is exactly where it is frame by frame. And you can just go through and plot it frame by frame, and then once you get to back to that starting point, that wherever you are is t, and then you can figure out where 1/2 t and 1/4 and 3/4 t are, and you'll be able to see how that graph connects. It should be a sine wave, or pretty close to a sine wave, right? Yeah?
What causes the pendulum to slow down a little bit, and can you predict it?
Oh, so that's just, yeah, so there is energy loss in these pendulums that is, it's a function of the material, so there's like stretch, like the string is stretching and unstretching and stretching and unstretching, so there's thermal energy, there's air resistance, and I was geeking out this morning actually and looking at pendulums. Like, people have developed pendulums that are accurate to within 1 second every year. The best pendulum ever made was built in like 1923, and it involves like, it's got one set up in a vacuum and then another one that's not in a vacuum, and it keeps time to within 1 second every year, which is just astounding. But yeah, it's effectively the principle here works on conservation of energy, and so the reason that it doesn't that it loses oscillation distance is because it's losing energy to the surrounding air molecules in the form of heat, largely. Yeah. All right, so your next job is going to be to compare equations and then to make a graph of position versus time.